Yes, in this video, these are the scope of what we're going to cover in these videos, and we're going to explain them in details. And this video is just one of the series of videos that's going to come on electrochemical cells. And as you can see, I will start with galvanic cell. And remember, when we say electrochemical cells, we have galvanic cells and we have electrolytic cell. Galvanic cells and electrolytic cell. So let's go to definitions. Okay, in this video we are going to explain how to use standard reduction potential table. And the very important thing I want you to know is that all the things we have on the left hand side here, the species we have on the left hand side here, they represent the oxidizing agent. And the ones we have on the right hand side, you can see here, they represent the reducing agent. That's number one thing we have to know. And also very important, I'm using table 4A. You can also use table 4B, but take note that the information will be the opposite. So in order to explain this table very well and master how to use this table, which is very important because it's going to give you a couple of marks, it's going to give you a lot of marks in examination, let's consider two half reactions. Let's consider copper 2 ions. You can see copper 2 ions here, and copper 2 ions. I'm looking for zinc. Yes, let's also use zinc 2 ions here. So let's consider these two half cells. Assuming you have these two half cells, you will see that from the arrow here, you can see that copper 2 ion, see copper 2 ion here, is a stronger oxidizing agent compared to zinc 2 ion. Copper 2 ion is a stronger oxidizing agent compared to zinc 2 ion. And as a result of that, this reduction, there will be a reduction here. Remember that oxidizing agents are reduced. Oxidizing agents are reduced. Let's consider the reducing agents here. You can see I have a copper atoms, and you can also see I have a zinc atom here. If you compare two of them, you can say that zinc is a stronger reducing agent. Zinc is a stronger reducing agent, and remember, reducing agent, the one that is stronger, is going to be oxidized. So in other words, this reaction here, there will be oxidation here, and as you know, remember, we say oxidation always takes place at the anode. And here, like we said, here there will be reduction, and the reduction always takes place at the cathode. Reduction always takes place at the cathode. So that is basically how to use this simple table. It's very simple if you master how to use it. Remember, I don't want you to make very common mistake. Remember, when I'm comparing the species, I compare copper 2 and iron 2. I didn't compare copper 2 and zinc. So anytime you are comparing them, or whether you are asked why is reduction taking place here, you must compare either copper and zinc, or copper 2 ions and zinc 2 ion. Okay, let's go into details and see what happens in galvanic cell. It's very interesting. Still mistake here. Okay, in order to understand these processes very well, which are oxidation, reduction, let's look at this solution. If you look at the solution here, the blue solution here, I have a copper sulfate. So copper sulfate, and here I have iron metal. So this is the metal inside the copper sulfate, and look at it here. It's been, I'm zooming in to see what happens here. So let's go on a microscopic level. If you look at this solution, you will see that I have a copper 2 ion inside the solution. And that copper 2 ion, remember that I have a solution here. In addition to copper 2 ion, don't forget we also have a sulfate ion, but it's not included here because it's a spectator ion. It's not involved in this reaction. And this is our zinc metal. This zinc here, this is it here. So it has been magnified. So let's see what will happen. Let's see what will happen before we use it to explain all the processes. Let's observe carefully and try to explain what is going on. In these processes, you can see oxidation is taking place and also reduction is taking place. Can you identify the substance that is reduced and the one that is oxidized? Can you identify the substance that loses electrons and the one that gains electrons? Okay, if you look at it initially, you will see that we have a copper, we have a zinc atoms, and the copper 2 ion gains an electrons, and when it gains an electrons, it becomes copper atom. You can see it here. It's been deposited at the surface of the zinc metal. The copper 2 ion gains electrons, and because it gains electron, you can see that copper 2 ion is reduced. Copper 2 ion is reduced because it gains electrons. And the electron that is gaining, where is it coming from? It's coming from zinc atom. Zinc atom loses an electron to become zinc 2 ion. And this is a typical example of a redox reaction. A reaction in which there is a reduction, which is gain of electron. And remember, when substance gain an electron, what usually happens? There is usually a decrease in oxidation number. When a species gain an electron, there is usually a decrease in oxidation number. What are we saying? We are saying initially that copper is +2. Now the oxidation number here is 0. So you can see from +2 to 0, there is a decrease in oxidation number, and that's why this one gain an electron. Copper 2 ion gain an electron, it becomes a copper atom. Conversely, let's look at zinc. You can see zinc that was there initially. Look at it here, the zinc. The zinc here loses an electron. And when a substance loses an electron, there will be an increase in oxidation number. You can see the oxidation number of zinc was 0. Now it's +2. So this is exactly this simple reaction forms a fundamental, it forms a background on which we are going to discuss a galvanic cell and all the electrochemical cells. So at the end of the day, you see what will happen, that the copper ion, brown copper ion, will be deposited on the zinc rod. Like I said, it's a redox reaction. Let me repeat it again because I want you to pay attention in details and see what happens. Let's watch this. Let's watch this. You can see. You see what happened? That copper 2 has turned to copper. It's being reduced. Let's follow this. Let's follow this carefully. Let's follow this. You see what happens here? It's being reduced. So the reactions, the oxidation and reduction are taking place simultaneously. So that's why we call them a redox reaction. So anytime we talk about redox reaction and we represent reduction half cell, oxidation half cell, let's understand that the reactions are actually taking place simultaneously. Okay, let's look at this example. You can see here half copper and half copper here. There is no current flowing because there is no difference. There is no EMF. The EMF is 0. There is no gradient in potentials. You can see. So because I have the same thing here, the reaction will not take place. The EMF will be 0. Bear that in mind. Let's consider another example. And this time around, our rod is still the same, which is zinc. Got it here. Still the same, but our solution has changed. Our solution now is silver nitrate. Our solution is this silver nitrate. You can see silver 1 ion, and this one is the copper. So look at it carefully. Can you predict the one that will be reduced and the one that will be oxidized? You may pause this picture, this video, and check your standard reduction potential table. You'll be able to predict, because you're expected to know using the standard reduction potential the species that will be oxidized and the one that will be reduced. Take it carefully and consider all the things we have said. Remember, we say on the left we have the oxidizing agent, on the right you have the reducing agent. Okay, let's go and see, and you see it for yourself. Let's go. Observe it carefully. What do you observe? You can see that silver ions. See silver ions here. You can look at this silver ion here. See, it gains an electron. The silver ion gains an electron, and the zinc loses an electron. So silver 1 ion is reduced, while the zinc is oxidized. Okay, another one taking place here. Let's follow this one and see what will happen. Let's follow this and see. Let's follow one of the zinc and see what will happen. So if you look at this, anytime you see this, you will know that the silver is reduced because it gained an electron. Look at it here. Silver is reduced. And remember what we said, reduction is decrease in oxidation number. The oxidation number was +1, now it changes to 0. That is decrease in oxidation. That is decrease in oxidation number, and that's what we call reduction. Similarly, you can see the zinc. Zinc loses an electron. Zinc changes from 0 to +2, which is increase in oxidation number, so it's oxidized. So using this method and the standard reduction potential table, it's actually easy for us to predict which substance that will be reduced and which one that will be oxidized. Okay, let's summarize everything we have learned. You can see the diagram of a galvanic cell, like I told you before. You can see the potassium chloride, the zinc anode, the copper cathode, and you can see this is a positive electrode, and the anode here is a negative electrode. And here we are using 1 mole of zinc sulfate and 1 mole of copper sulfate. Now let's look at this cell notation here. The cell notation here, remember that here what we have here is oxidation. So what happened? This is the zinc solid, which is this one, the zinc solid. This species, you can see this arrow means phase change. It's changing from solid to aqueous. This line means there is a phase change. It's changing from solid here to aqueous solution. So you have the zinc in solid 2, zinc 2 plus, zinc 2 plus, which is in aqueous solution. And we have the symbol here to represent the salt bridge, the symbol there to represent the salt bridge. Then the same thing happens here. The copper 2 ions, which is in solution, to copper metal, which is in solid solution. Also, this one represents the phase change. So you can see in this very example, all the electrodes we are using, they are both active electrodes. They are both active electrodes. So we see one of them is here and one of them is there. So this is our cell notation, a simpler way of representing this diagram. Oxidation, which takes place at the anode. So whatever that's happening on this left hand side here is the reaction, the half reaction taking place at the anode. And on the right hand side here is the right half reaction taking place at the cathode. Yes, I'm going to do one more example. Remember, there will be some example where we have to use inert electrode. Okay, let's consider this galvanic cell here. If you look at it here, I have zinc electrode in zinc ion solution and copper electrode in copper ion solution, which is very important. Make sure two of them will match at all time. And I have the salt bridge. And the commonly used salt bridge is the potassium chloride. So let's notice we have a potassium chloride here. Remember, potassium chloride is going to dissociate, so we have calcium, we have the cations and the anion, the potassium ion and the chloride ion. Bear that in mind. And you can see, as you have explained earlier, you will notice that the process that is taking place here is oxidation. There is loss of electron. And here, the process that is taking place here is reduction, because there is gain of electron. Remember, we say anytime there is a gain of electron, there is always decrease in oxidation number. Anytime there is a loss of electron, remember, this can see here, this oxidation. When there is loss of electron, there is always increase in oxidation number. So because the two half cells are separate, remember in the initial one, the initial reaction which I used to represent them, all of them are happening in one container, but now we have separated the two half cells into different compartments. So because they are taking place in two compartments, you can see that we are channeling all the electron that was produced. Remember previously the electrons, we just moved from copper to this. Now all the electron that's being produced, they are being channeling them through the external circuit in order to generate electricity. And that's why we say that in galvanic cell, we are using a spontaneous chemical reaction to produce electricity. You can see here from chemical energy here to electrical energy. So it's not difficult for you to remember, because we are using a spontaneous chemical reaction. We are using it to generate electricity, to produce a current here. So you can see the two electrons that is given out when oxidation takes place, they move through the external circuit and they comes here, and we are gaining electron, the same electron that the copper 2 ion is gaining. So if you notice at this reaction, you will notice that in this compartment we always produce zinc 2 plus. So the positive ion are building up here. I hope you understand what I'm saying, because we are always moving from zinc, which is a neutral atom, to zinc 2 plus, which is in solution. So there's a build-up of a positive ion here. On the other hand, conversely, if you go to the other side, you are saying you are removing positive ion there. So as a result of that, the negative ion will be building up here. The negative ions are building up here, and the positive ions are building up on this half cell. So, and that is exactly one of the important functions of the salt bridge. Because salt bridge, yes, primarily it completes the circuit, but in addition to that, it maintains electrical neutrality. And when you maintain the electrical neutrality, because the positive ions are building up here at this compartment, you can see that the anions, remember this is the anode, the anions will migrate here to neutralize the excess one, and here the cations will migrate here to neutralize the excess negative, so maintaining that electrical neutrality of a galvanic cell. So this is a very simple process that we should be able to understand and be able to write the different half cell that is taking place using standard reduction potential table. Remember, we said this reaction this thing is something that you can actually carry out in the laboratory. And when we are carrying out in the laboratory, the condition must be in standard condition. And when we say standard condition, we are saying that the solution we are using here must be 1 molar. In other words, 1 moles per dm cube. So if we are using copper sulfate, we must weigh in the molar, we must calculate the molar mass of copper sulfate and dissolve it in 1 dm cube of water. The same thing happening here. If we are using a zinc sulfate, we must calculate the molar mass of zinc sulfate and dissolve it in 1 dm cube of water in order to form 1 mole per dm cube of the solution, which is one of the conditions that we normally use to produce it. It must be in standard condition. In addition to that, the temperature of the environment must be 25 degrees Celsius, which is 298 Kelvin plus 273. So if you look at this here, these are basically the two conditions. I don't know what I want to talk about the pressure here because there's no gas involved. But in some reactions you might see a gas. But we're going to look at some other reaction where gases are involved. So those are the two conditions that will be involved in this cell. So you can see as the current, as the electrons are producing here, that's why we are producing current. So anytime you are using a battery, I think you'll be able to appreciate it very well and know in details the reaction that is taking place when you are using a galvanic cell.